Thank you, Damien, for this introduction. Let me share the screen. Okay. So I'm super happy to be here today to speak about code as graph data with you and what is the knowledge graph of software. Let's dive into it, but starting with a small historical inspiration. So you might know that before 1945, in the beginning of the computing era, computers or big mainframes, mechanicals mainly, had two physical distinguished space where to store memories. So you had on one side the program instructions and on the other side data. So it means that instructions could manipulate data but could not manipulate instructions themselves. And in 1945, John von Neumann came with a first draft of report on the EDVAC being one of the big computer of that age. And he came with a big innovation, which was the idea of having a unified memory where to store data and instructions. That memory would be addressable, so instructions could start changing the instructions themselves. And this is the first time when we really thought about code or instruction being data, right? It brought a lot of flexibility because programs were suddenly able to actually change themselves. And it might look super normal or simple to you because it is actually what we use on all our, the architecture used on all of our devices today, but it was quite a big change at that time. So this leads me to today. It's always interesting to see what we have in the past to fine-tune the future. But today we have Neo4j, we have great software to store graphs. So we can go further and think about software or code as being graphs. So, when you write software in any programming language, you might know, you are using plenty of various entities of different natures, like variables, classes, functions, call of functions, types, and all of them are actually interconnected. So why are we storing those things into text files, right? It's like reading text, and then you have to rebuild that graph into your mind to understand what are the links between those entities. So the way I see a software is a complex graph. And I like to say it's even more than that. It's like a multidimensional graph, not in a mathematical way, but more because there are many ways to see there are many perspectives to read that graph. Depending on who you are, what you are, you might not look at the graph the same way. Typically, a compiler will look for the abstract syntax tree, right? It will try to reconstruct the structures so it can transform your program into instructions. But an architect would maybe look at the documentations, the APIs, and how they interact with each other. What is the architecture of your program, of course. So there are a lot of metadata hidden within your code, and they are interconnected with each other. When you think about software as a graph, it opens a lot of new possibilities, like it was in the John von Neumann age. It brings a lot of flexibility because suddenly you can query your graph. You can audit what is inside your software. It's not just about text. So code is graph. But what makes a good software? It's not always easy, and there is no magic answer. There is no magic recipe to build a good architecture. But one good way to start is actually to focus on data, because a software is about information. It's about automating something that you would do by hand, but it's really data is really the core challenge of any software. So you focus on data, looking at where it comes from, what are the inputs, and how it should be transformed. So at Olymp, we like to promote the data-first methodology. This would be a good start to create a solution that would fit the needs of your customers, typically. So data-first methodology requires to iterate from a small MVP where you manipulate directly relevant data, not just mockups focusing on UI. No, you directly give to your customer, to your client, something that will solve one of his issues. So you can iterate with him and construct from there appropriate software. To do that properly, you will need to define data flows. So this is a way to draw the flow of data to discuss with your client or with the customer what will be the transformations of your data. And to be able to draw and diagrams with data flows, you will need abstraction layers. You will need to be able to think about your solution from a higher point of view, from a business point of view, instead of directly going down and up to the implementation, technical details and so on. So it requires abstractions, which means a good architecture with layers. And to implement that those abstraction layers, you will need to apply the encapsulation principles. What is good is that encapsulation is something that we learn, everyone at school, when learning computer science. So it's not completely weird for us, but this is really important to apply on our softwares. So thinking about encapsulations, to be able to create abstraction layers, to think on a higher level to create data flows. Okay, and encapsulation means what? It means having little pieces of code, little pieces of items, independent items that will be orchestrated through those data flows. So this is somehow a good recipe to have, in the end, a proper solution. So we have two things: software, which are graphs, and to make a good software, we need data flows and abstraction layers, so encapsulation, right? So how do we do that? Thanks to the code composition paradigm. So this is something that we came out at Olymp. You probably have heard about composition those last years because this is coming more and more trendy, let's say, not only AI today, also composition. We are doing composition everywhere already, like in the UI. Typically, we have web components. A lot of libraries are trying to split codes into smaller things, you know, to divide and conquer. But code composition goes further than that, because yes, you start here with a lot of independent pieces of code, well defined, but could be different natures, like algorithm, very simple mathematical function, could be a UI components, any kind of things in your favorite language. And then we will bring the graph. So for that, we have a language which is designed to do composition, code composition. And the first piece of that language would be to wrap all the independent pieces of code. Okay, and those things, I will name it as technical capability. It's just a capability, because suddenly it becomes something that you can do with it. It is something that just execute a contract. If you give it inputs, it will give you outputs that are well-defined, well-known, and you can wrap it inside those, let's say, boxes, okay? And those boxes comes from, as the smallest piece of that language. They standardize your code. And once you have that, you can start composing and creating abstraction layers. And with those boxes, you just have to draw your data flows, building more abstract and more abstract capabilities, which will become more and more business oriented or more and more close to the final solution, right? So you start from your technical items, capabilities, and you go up and up closer to your solution to, at the end, get your applications, right? So when you have your full data flow defined as composition of composition of composition, you have your application. It's as simple as that. All those layers are just about nodes with characteristics connected to each other. So it's a graph. And that language is really designed to be stored as a graph in a database, so in Neo4j. And in the end, when you compose and you have all your applications built like that, it suddenly becomes the knowledge graph of your IT landscape. Because you will know where pieces of code, where that piece of code is used in your entire landscape. You will know that if you change a little bit the signature of one component, what impact it will have. And you will also be able to extract directly your architecture diagrams. You will be sure that if you have drawn a data flow to solve a solution, to solve a problem, sorry, for your client, actually that data flow is actually executed, and it is the implementation. So this is why it's so powerful. And on top of that, of course, it uses Neo4j, so that's powerful. But this is the theory. But how does it work now in real? So we have Olymp. Olymp, of course, implements the code composition paradigm. And like for any programming language, we need three things. First, a place where to store that language. I spoke about it a few times. It's Neo4j, and we call it the composition database. We also need something to execute and transform that language into program instructions. This is our runtime agent, which is a lightweight agent just deployed everywhere you want. It can be a backend in the cloud. It can be a desktop application in your browser or whatever. It can be on the edge. And finally, you have, of course, the IDE, which helps you to compose and write your code. Since it's a bit more complex as a human to write queries, transaction into Neo4j, we won't write them manually. The IDE, the composer, so named draw, will do that for you, and you will be able to draw actually your data flows. Okay, and draw is able to import your code and wrap those pieces of code into those boxes that standardize and well-defined what are the inputs, what are the outputs, and how to compose them into the database. You can think about those boxes as pointers. It's really pointers to pieces of code that could be on any repository, Git repository of your company or whatever. Okay, so let's try it for real. I prepared a small demo. Here on the left, we have draw. It's a very simple function, but it is already a box. So as I said, it has inputs, here only one number, it has outputs on the right. And inside that, you can draw your data flows. Whatever data will go through. Today, we will just use numbers to simplify a little bit the demo. Within that editor, I can drag and drop capabilities from the catalog here on the right, and then plug them together. But I won't do that here right now from there, because I want to show you another way to do it, maybe a bit more like Inception. You can directly write some code from the application itself. So that's the idea. I will show you how it works. So on the right, we have an app that is actually executed by our runtime, and it's running right now. I see that somebody is already using the app. So that application is designed to just transform some numbers, which are generated here on the top. And those will be transformed by the flow into other numbers using that function here on the left. So even though the flows are not connected, so we can see here that I could finish the flow, eh bien, that function is actually already used inside my app, just it is disconnected. So now, yeah, if you want to try, you will see, if you open the app, you see this small content, and you will be able to create just a transformer. I will do it as well with my name. And I want to multiply all the numbers by, let's say, 8. And I will add some documentation because the documentation is interesting. It's here a way to show you that we can indeed add some metadata directly within the graph, even though I am running the app. So here I will just add, so multiply the input by 8, and I create it. Okay. So I see that you got a lot to play with it. There should be some maximum, so it should stop working for the others at some point, but this is normal. So here I see that, for instance, Dania has created a transformer. It has probably some documentation here. I see multiply the input by 5. Cool. Okay, I will try to use it. And we see that indeed it worked. It detected automatically. This is thanks to the fact that we are actually reading live the graph, so the code changed live. This is fine. But on top of that, we also have here the documentation. And as I said before, if you remember, as a compiler or runtime, I don't need documentation. It's not my thing. I just need the execution part of the graph. But here, since it is in the same database, it's the same memory. So the runtime has been able to query that specific part of the graph because I asked for it specifically. To give you an example, I think in Java, you wouldn't be able to query the code to get to the Java doc of a function. Of course, you wouldn't do that, but here it's just to push the example to the end. So let's try now another one, like boom transformer, just to show if it works. Okay, great. And that's the thing, I guess it divided by 10. And let's do a third example. Okay, no documentation for this one. But that's the idea, you get it. And here, what I would like to show you now is inside Neo4j, because we are Neo4j conference. And yeah, it's a big graph, but I will zoom in a little bit right after having done that, because it looks better like this. Okay, so we have here on the right, this is actually the node that represent my function that I just edited. And as we can see, it runs here a lot of other items. Those are calls of other components definitions. And themselves, they all have a documentation here, object. Okay. And inside, they will run another function, which is either plus, divide, multiply, and nobody use subtract. But if I show you, again, here in draw, I can enter within Dania transformer we used before, and here we see the other level. So we go inside one abstraction layer, and we see here that we multiplied by 5. Okay, so this is just to illustrate the concept. Of course, in general, we manipulate much higher level object. You can create data types and store them in multiple databases. But here, the core concept is that your code is graph data and stored like that. Okay, so this is the lamp. I cannot speak about code composition without speaking about AI, because AI is so trendy today that I must speak about that. And what is nice is that code composition actually enables somehow the AI, because you know that AI is super good at generating code, algorithms, even images, like you can see on the right. When you really define the problem to solve in a good, in a standard way, let's say, with all the inputs, you say, okay, when this is the format of my data, and this should go out of it. Okay, then it can realize the algorithm. But as soon as it becomes more complex, because you explain, I don't know, business case that you want to solve using multiple data sources, or exposing APIs and doing a lot of stuff in your software, then the AI won't be able to actually go to the lowest level, getting the appropriate libraries written in your favorite programming language, to then connect them together, creating abstraction layers and connecting all of that together to build the solution on its own, right? So AI is good when a context is well defined and the problematic is quite small. So good, let's use code composition. Since we split all the problems into smaller ones, and then we compose them. And as soon as you created a catalog, maybe with AI, and that's actually what Laurent is doing when he has time, you complete your catalog of capabilities thanks to AI, you standardize the way of using them, and then you go up to a next abstraction layer. And again, you can use the AI to say, okay, now that you have all those things that you can use, please put them together to solve that specific problem. And going up and up and up and up, and like this, you compose with AI things that AI has composed, and etc., etc. So it's really quite complementary. Another way to use AI with data flows is that we have packaged quite a few AIs into capabilities. So it becomes super simple, to actually query AI within the context of a data flow. So typically, if you have a data source with unstructured data and you want to transform them to a more structured way without using a handwritten algorithm, and want to use AI for that, no problem. You just drag and drop the AI capability, you give instructions, and inside the data flow itself, the AI will actually transform your data and then push it back to further to the next step in the data flow. So this is two ways to use AI complementary with the code composition. So that's it. I hope you enjoyed learning what is code composition, and please come and join us on Discord, ask questions. You can also join the community and draw for free, create your capabilities, share it with the community. And I don't know if you have questions, but I would be glad to answer them. Laurent, maybe is there any questions open?
Yeah, there is one question from Gabriel Bergquist about the state of the art of using the LLM to import large code base into a code composition platform, if I understand the question correctly.
So if I understand well, the idea would be to use LLM to split the code into small capabilities. And then from there, it becomes super easy indeed to import that into, to transform them into what we call bricks. So those small technical capabilities. Actually, that kind of tool is really part of our roadmap for next year. We would like to join. So that's why I said the future of code composition with AI. There are plenty of things to do with that. And what you just said is actually one of our main challenge now. Be able to reuse and import existing code, to split it in a smart way, so that it completes your catalog without having to redo or split it by yourself. So it's not yet possible with a tool like this, but it is coming.
And since we're on a Neo4j conference, there is as well a webinar that we'll organize on using business data in Neo4j from composed build applications. And so that we don't have the date yet, but if you follow us on LinkedIn, you will be able to get the date when we'll do this webinar. So what it means is that you would be able to leverage this approach to build applications with your data that resides in Neo4j. And I'm sharing the LinkedIn page so that you can follow if that's it interests.
Okay. Any other questions? If not, maybe I can show you something else here. I have just to show you an example of coded capability that has been wrapped into what we call brick. But here, actually, it is an auto-completion made by ChatGPT. So we just import the OpenAI library, and from there it's just classical JavaScript code, right? And you will see that here there are a list of inputs. So you can directly ask for the prompt, choose your model, etc., some options, and you will get the answer from GPT. And starting from there, so here you have the implementation. You can call any kind of library you like. And then within Draw, you have the exact same structure, contract with the inputs and the outputs, and you can just plug your data flows, and that's it. So it's really super simple to wrap any kind of existing libraries. And this is what we want to automate as well with AI. Okay, so I guess that's it. Thanks a lot for listening to us, and see you around.
Thank you very much.